In this video, we are going to be learning about nuclear fusion and nuclear fission. We're going to be learning about some positives and negatives of each and how to do certain energy calculations of both. So let's start with fission. What is nuclear fission? Well, nuclear fission is the splitting of a large nucleus into smaller nuclei. Or in other words, the splitting of one large atom into many smaller atoms. Now, one thing with fission is normally when we have fission, more neutrons are given off, which could then cause a chain reaction and more fission to occur. But before we get into that, let's talk of where fission is used. Fission can be used both positively and negatively. In power plants, we tend to use fission in a very positive way, where we use fission on uranium to create energy. Where it's used negatively is in certain things such as atomic bombs. And we'll learn about the energy of both of these throughout this class. Fusion, on the other hand, is also both beneficial and it's been used negatively as well. Fusion is when two low-mass nuclei combine to create a larger nuclei. So in other words, we're forcing two nuclei together to create a new nuclei, and which creates energy. So where do we see this? We see this in the sun, which has many positive benefits, such as the energy from the sun gives us photosynthesis and many other things. It allows life to happen on Earth. But we have also seen it used negatively in things such as hydrogen bombs. So let's look at this example here. It wants us to complete the following reaction. But before we get to that, let's try and figure out what kind of reaction it is. I look at this, I have uranium-235 interacts with a neutron. When it interacts with the neutron, we end up getting barium-144 and some unknown element, and we get 3 more neutrons. Well, I look at this, the uranium-235 is breaking down. So that means we're undergoing a fission reaction. Well, what is this mystery atom? Well, first of all, we know my atomic mass number cannot change. My before and after must equal the same. So in other words, I'm going to have 235 plus 1, and then we're going to minus 144 minus 3 times 1, and that's going to give me a total of 89, because I took all of my atomic masses to figure out what is this one. So I'm going to have some atom with 89 nucleons. Now let's figure out what is going to be my atomic number. And my atomic number has to stay the same, because we're not going to be destroying or losing any protons. So I have 92 there and 56 here. So I'm going to go 92 minus 56 is going to end up giving me 36. Now I look up what is element 36. That is going to be krypton. So right here we're going to end up getting krypton. Now this is, like I said, a type of fission. So where do we see fission? We often see it, like I said earlier, in power plants. So how does that work? Now if I look at this here, these red bars here, these are going to be uranium-238 or radioactive uranium bars. Now, what ends up happening with these uranium bars is when one of these bars start undergoing fission, it's going to shoot off 3 neutrons. Because if we look here, we have 3 neutrons being shot off. So we end up with 1, 2, 3 neutrons being shot off in different directions. So let's draw that out here. When we draw these, we're going to end up having 3 neutrons being shot off. So I get 1 neutron shot into there, another one, and another one. And that's going to cause a reaction in this uranium rod as well. Now from here then, we're going to get 3 from this first one being shot off, and then we're going to get 3 from the next one being shot off, and so on. So we end up getting something called a chain reaction. But now here's something interesting about these nuclear reactions in power plants. These neutrons are going so fast that they actually go through and they don't react with the other uranium. So how do they make it react with the other uranium? They must slow down these neutrons. So that's when they put a graphite coating over their uranium. So when they put in a graphite coating, that's enough to slow down the neutrons so then they could react with the uranium, causing this chain reaction to occur more and more and more, and it causes the action to speed up. Now, what happens when these get too hot? Well, then we have these other metals that are very stable that drops down and it absorbs all of the neutrons that are being shot out from our fusion. So that's in general how these nuclear reactors work and how something called a chain reaction nuclear fission occurs. And it's very easy to get out of control. So the graphite or heavy water that is used to slow down neutrons in order to react with the uranium and create a chain reaction, those are called moderators. Control rods are those rods that we bring down to absorb neutrons to control or stop the reaction. And we normally use metals such as cadmium for that. Now, fission reactions can create tremendous amounts of energy simply by looking at Einstein's equals mc equation when we're looking at the mass defect of what's happening when the fission process occurs. So according to Einstein, a nuclear reaction mass is not conserved. The difference of mass must be because some of the mass is converted to energy. So here's a question for you. What is the difference between fuel and spent fuel? Is it A, fuel is rich in cesium and the spent fuel is not? Is it B, spent fuel is rich in uranium and the fuel is not? Is it C, the mass of the spent fuel is less than the mass of the fuel? Or is it D, the mass of the fuel is less than the mass of the spent fuel? Well, in this case, the mass of the spent fuel must be less than the mass of the fuel. And that's why there's so much energy given off, because of the mass difference. The mass change or the mass defect is the energy of what's happening. So now let's try and find the energy produced by nuclear fission of uranium-235. So in this case here, we have uranium-235 reacts with a neutron. So a neutron is being shot into uranium-235 to produce barium-144 and krypton-36 and then 3 more neutrons. We want to determine the energy of this reaction. Well, my information is given here up above. So I'm going to use that information to help me. Now remember, when we're looking at this, we're going to be looking at my mass defect. So first, I want to find my initial mass, which is going to be my mass of the uranium-235 plus my mass of the neutron, which is going to be, from my information above here, 3.929 times 10 to the negative 25 plus 1.67 times 10 to the negative 27. And when I add that together, that's going to give me 3.19194649 times 10 to the negative 25 kilograms. Now, let's find my mass of my products. So here we're going to look at the mass of barium-144, which is 2.3898 times 10 to the negative 25, plus the mass of krypton, which is 1.4765 times 10 to the negative 5, plus 3 times the mass of my neutron. Now, when I add these all together, I'm going to get 3.196547 times 10 to the negative 25 kilograms. So now that I have my two masses, I'm going to subtract these masses to get my mass defect. And then from there, I can figure out my energy. And that's going to end up giving me 3.102 times 10 to the negative 25 kilograms. So now that I have my mass defect, I can end up finding my energy by using my energy is equal to mass, my change in mass, or my mass defect, times the speed of light squared. So my mass defect was 3.102 times 10 to the negative 25 kilograms, and we're going to times that by the speed of light squared, which will end up giving me 2.791 joules. So once again, nuclear fusion is the exact opposite of nuclear fission. So instead of separating atoms into smaller atoms, what we're doing is we're combining small nuclei into a larger atom. So where we see fusion is in the sun, and that's the only place where we're getting useful energy from fusion so far. Well, we have used fusion, but not really in a positive way, as we've only really been able to use it in the hydrogen bombs. Now, let's take a look at a fusion energy conversion here. So I want to know what is the energy that's going to be converted from this fusion. So here we have deuterium hydrogen and tritium hydrogen being fused together to produce helium and a neutron. So once again, we have to find our mass defect. So first we must know our initial mass, which is going to be the deuterium hydrogen plus the tritium hydrogen. Now, by looking up, I could find the masses of both of those. The mass for the deuterium hydrogen is going to be 2.014102 atomic mass units. And my mass of my tritium hydrogen is going to be 3.016049 atomic mass units. When I add these together, I'm going to end up getting 5.030151 atomic mass units. Now let's look at my final, the mass of my final product. So here we have a helium, so we want the mass of a helium, and then we're going to add the mass of a neutron. So in this case here, we know the mass of helium is going to be 4.002603 atomic mass units. And we know the mass of a neutron is 1.008665 atomic mass units. So we're going to end up getting 5.011268 units. Now let's look at my mass defect. My mass defect is going to be my initial mass minus my final mass, which we're going to end up getting 5.03151, and we're going to subtract 5.011268, which will give me a total of 0.018883. Now, if we want to make this, we're going to use this one in electron volts. I'm just going to times it by 931.5 electron volts over my units. These will cancel off, and that's going to end up giving me 17.59 mass electron volts. Now, some of you might be thinking, how is it possible that for some atoms, when we combine them, we have a mass defect, while with other atoms, when we separate them and split them up in fission, we have a mass defect? So for some atoms, we get energy from combining, while others, we get energy from separating. Well, this table will help us understand that. Basically, the more binding energy per nucleon, the more stable the atom is. So my y-axis in this here is going to be my binding energy per nucleon. And my x-axis is the number of nucleons. Now if we look at this here, my optimal, or my highest amount of energy, or binding energy per nucleon, is iron 56. So it's element iron 56. Now, so if we look at this graph, if I combine two deuteriums, I'm going to get a whole bunch more binding energy when I get helium-4. That's a huge increase in binding energy. Or in other words, my mass defect is going to be pretty big, which gives me more stable. Now, eventually there's a little dip here down, so we're going to ignore that, but then eventually we could go to carbon right here, and carbon has higher binding energy per nucleon. Remember, this is per nucleon than helium. So that's why these here, and look at how steep and how much gaining of energy there, that's kind of showing how fission produces quite a bit more, or fusion produces quite a bit more energy than fission, which is on this side. So this side here is fission, this side here is fusion. My graph is a lot steeper on the fusion side, especially for the smaller atoms, which shows that we're having more energy given off. And if we're looking on the fission side here, as uranium-238 moves up, we're getting more binding energy per nucleon, which means we're gaining more energy as it breaks down, and it wants to become stable, and iron 56 is the most stable. So that is again once why this side is going to be fusion and this side here is going to be fission. If we look at the graph on the previous page, it kind of explains why hydrogen bombs, which is fusion, are more powerful than fission, or atomic bombs, which are fission. Because the hydrogen bombs, when we have fusion, have a lot steeper slope compared to the atomic bombs, which is fission. Now here's something interesting to look at. 1 gram of fuel from a fusion plant can produce 90,000 kilowatts of energy. That is the equivalent of what it would take 11 tons of coal combustion. So if fusion is such a powerful source of energy, why don't we use it? I mean, it's used in the sun. We know it can be used or it can be created. But the problem with this is we need a lot of energy to create fusion. We need to suspend the hydrogen atoms in air and force them through with enough speed, so we have sometimes a ring where it forces the hydrogen atom with enough speed so it collides with each other to create fusion. And we need enough there to create a chain reaction. We saw how easy it is to create a chain reaction with fission. After all, 3 neutrons are getting let off most of the time that interact with other elements to create a chain reaction. But for fusion, it's a lot harder. We need a lot of kinetic energy of the hydrogen. And the problem is, if that hydrogen hits any little particle, it loses its energy and the fission process will not happen. So that is one of the main problems with fission and why we're having such a hard time harnessing the power of fission to help us power our future better.